Have you ever imagined how the bright light that shines on Earth at night was formed? Well, there have been several different formation theories for the moon proposed by scientists. And in today's video, we will be discussing how the moon was formed. The moon has inspired billions of people to gaze upward in awe as one of Earth's most familiar sights in the sky. We created tales about the silvery orb early on in human history, and later we waged a space race to explore it on foot. There was always one unsolved question. How did the moon develop and find a home around our blue planet? When the Apollo astronauts returned from the moon in 1969 with around 48 pounds of lunar rock and dust, they kicked up the scientific inquiry to find an answer to this question. Scientists discovered that the moon formed around 4.5 billion years ago, during the turbulent early years of our solar system's creation, by analyzing the age of the rocks. Today's technologies and procedures can examine the chemistry of lunar material in ways that were unthinkable just 50 years ago, giving more information about our moon's history than ever before. According to the capture theory, the moon was produced elsewhere in the solar system as a wandering body, kind of like an asteroid that was captured by Earth's gravity as it passed close by. The accretion theory, on the other hand, proposed that, the moon was formed at the same time as the Earth. Finally, the fission scenario states that Earth was spinning so quickly that some material broke away and began to orbit the planet. The giant impact idea is the most widely accepted today. It is suggested that the moon arose as a result of a collision between the Earth and a planet the size of Mars. The moon was formed when the debris from this impact gathered in an orbit around Earth. The giant impact hypothesis. A large asteroid known as Theia collided directly with Earth 4.51 billion years ago, when our planet was still developing to its current size and producing its core, according to the widely accepted scenario of the moon's formation. The resulting impact melted a portion of the early Earth's mantle, throwing rocks and gases into the atmosphere. The ejected matter, a mixture of material from Earth and Theia, began orbiting our planet after some time. Clumps of gas, dust, and rock met and became trapped together. They formed a spherical shape that continued orbiting Earth after just a few thousand years. Recent simulations reveal this as a very short duration. It took 150 to 200 million years afterwards for the early moon rock to cool and consolidate into its distinctive gray, stony appearance. Our planet's creation was also aided by Theia, which pushed heavier elements such as nickel and iron toward the core. In an email to Popular Mechanics, geochemist ERICK CANO of the University of New Mexico in Albuquerque says, "Over the last 50 years, the giant impact hypothesis has become the favored explanation, which I believe is the best approximation of what likely happened given the geochemical data that we have been able to collect." While the giant impact hypothesis is widely accepted, there are still many unanswered questions about the moon's past. According to Anthony Gargano, another geochemist in the University of New Mexico, the main obstacle for planetary scientists seeking to reconstruct the narrative of the moon is that their signals originate from very processed rocks. Since its inception, the moon has gone through billions of years of alterations. The rocks on our spacecraft were altered through vaporization, magma, and crystallization. Fortunately, technology to measure planet formation is rapidly improving. Scientists can now measure chemical compositions in ways that they couldn't back when Apollo was launched. For example, we can now use an electron microscope to investigate a slice of moon rock or atom probe tomography to study a grain of moon dust. The atomic level variations in materials are distinguished using this method. The measurement of stable isotopes is also very useful. For example, there are two types of oxygen, light and heavy. The heavy version has 2 more neutrons in its atomic nucleus than the light version. The amount of each isotope found on lunar samples provides more about the processes that shaped the moon's environment. According to CANO, early investigations assessed the average value of oxygen isotopes in lunar rock found in a variety of lunar areas. Scientists now know that the results of those studies were misleading because they averaged the measurements. The measurements indicated that the moon's chemical composition was virtually identical to Earth's. But that evidence refutes the idea that the moon contains material from a secondary body colliding with Earth. The delivery of oxygen by meteor strikes is one explanation for the chemical composition similarity. A study that was published in March of 2020 clarified the situation thanks to a new approach that looked at the same samples. CANO and other researchers evaluated each sample separately using high-precision measurement instruments, finding distinct traits in each one, according to the findings that were published in Nature Geoscience. The Moon appears to have different oxygen isotope compositions than our Earth, according to scientists. This evidence, discovered in samples from 30 miles beneath the surface of the Moon's mantle, supports a large impact theory. This also elucidates more about Theia, the enigmatic figure. Our findings imply that the moon-forming impact did not completely homogenize the distinct oxygen isotope compositions of Theia and Earth, the researchers wrote in their paper. This provides quantitative evidence that Theia could have formed farther from the Sun than Earth. So how did the early Moon appear? Researchers in Germany discovered evidence that the Moon took shape just a few thousand years after the collision. Ejected debris from Theia and Earth solidified into a molten ocean 600 miles deep, according to the study, which was published in the journal Science Advances in July of 2020. According to the computer simulation models that researchers employed in the study, it took 150 to 200 million years for the liquid rock to entirely crystallize. According to previous estimations, the Moon cooled into a solid crust about 35 million years ago. The Moon's surface, unlike the Earth's, did not cool enough to form tectonic plates. Rather, it had a thick crust composed almost entirely of feldspar, a light-colored mineral. The bright areas we can see on the Moon now, sometimes known as the lunar highlands, are made up primarily of feldspar. Most of us think of the Moon as a barren, gray world with craters and little else, but it was quite active geologically for much of its history. The Moon, like the Earth, began with a thick covering of molten rock on its surface. Now, we won't have to wait long for another batch of lunar samples to shed light on our unanswered puzzles concerning the Moon's formation. But let us know what you think in the comment section below, and give us a thumbs up by hitting that like button. Don't forget to subscribe to our channel and turn on post notifications so you don't miss any updates from us. Finally, go through the channel for more videos like this. Thanks for watching, and we'll see you in the next video.